So I'm going to try to stand close enough to this thing and my computer so I can click forward. But thanks for having me here at Evergreen Valley College. And thanks to everybody for coming out tonight. So it looks to be a little thin audience, perhaps because the weather looks like we're not going to be able to see any celestial objects. But in this kind of talk, you get something even better. You get to actually hold them in your hand at the end of the talk, because I actually have brought a couple of meteorites with me to share with you guys. So all the folks that stayed home because the stargazing was like, oh well, too bad for them. So the Antarctic Search for Meteorites is a trip that has been going to Antarctica just about every year since the late 70s. And the United States has been running this program. There's a couple other countries, including Japan, that also send teams down to the Antarctic to search for meteorites. And the program that the United States runs is led by Dr. Ralph Harvey, who's a professor at Case Western Reserve University in Cleveland. And the funds come from both the National Science Foundation, but mostly NASA. And actually the year that I went, which was in 2003, 2004, that our winter, but their summer in the Southern Hemisphere, they were able to send 4 extra people. It's usually a team of 8. And with funds from the National Science Foundation, they were able to, or actually extra funds from NASA, they were able to send an extra 4 people. And I wish I could say that there was some kind of amazing qualifications to go on this trip, but to be selected as a scientist that participates in this 2-month-long trip to Antarctica, your major qualifications are, one, is to be involved in some kind of research that has to do with space science, not necessarily meteorites, because I was not a meteoriticist, or am still not a meteoriticist. But the second qualification has to be somebody that they can tolerate being in a tent with for 7 weeks. So, you know, sometimes those two things are mutually exclusive. But so meteorites fall all over the Earth, and my parents were kind of wondering, you know, their daughter, oh my God, especially the younger of the two, right, the baby of the family, is going to this horrible, horrible place, right, where the early explorers suffered and died, and you know, and they're like, really? Well, where are you going to stay? And it's like, well, in a tent. And so the reason that we send people to the Antarctic to search for meteorites is that, even though meteorites are falling all over the Earth all the time at the rate of 1 per square kilometer per 10,000 years, and by one meteorite, I mean not just like a little tiny one, but something that you could actually pick up and see. And but what's special about Antarctica is that this polar desert environment serves to protect the meteorites in such a way that they never experience liquid water, because as we can tell from looking at the hills here in California, liquid water dissolves rocks pretty quickly. And so because these meteorites never ever experience temperatures that are warm enough to actually melt water, they're basically sitting probably in snow when they first fell, and then they've been entombed in ice for anywhere from, you know, a few thousand to up to, I think the oldest, or the longest residence time at the surface of the Earth is over 2 million years. So this polar desert environment not just preserves it, but it actually, the way the ice moves, it serves to concentrate the meteorites in certain areas. And then, of course, it helps that these rocks are kind of dark. In fact, they're sort of black because they've burned as they've come through the atmosphere at very high velocity. So they're kind of easy to see. You know, the ice and snow is very bright, white or blue, as I'll talk about in a minute. And the meteorites are black. So they're actually kind of hard to miss. So here's how we get to Antarctica. We actually fly out of LAX and fly down to Christchurch, New Zealand, which is a very lovely place if you ever get a chance to visit. And the United States Air National Guard actually flies these airplanes. These are LC-130s. You might notice that they have skis on them. And the skis are actually down all the time. They never get retracted. It's the wheels that get retracted. So when you take off from Christchurch, the wheels come up and they do not go back down until that plane gets back to Christchurch. So it's kind of an interesting flight. These things fly like kind of like a brick with wings, according to one of the pilots. And it's not exactly luxury travel, I can tell you that. You're basically, you know, it's cold, it's noisy, you're jammed in there with all kinds of cargo. There's nobody with the little drink tray coming around. And this is Mcmurdo Station, which is the main headquarters for the United States in Antarctica. So New Zealand and a couple other countries also have little stations, and as far as I know, Mcmurdo is the largest. And it's on Ross Island, which is actually not part of the main Antarctic continent, but this is very close to the place where the early Antarctic explorers like Scott and the other, like Shackleton, those guys, when they had their launching off point to strive towards the South Pole. And it's kind of weird. It's a combination of college campus, military base, a small town. And so basically about 1,000 people live here during the field season, which lasts maybe roughly 4 months, from mid to late November until early March. And if you're not out by early March, you are spending the winter. And so most of the scientists and most everybody else gets out at that time. And then there's a skeleton crew that just kind of keeps things running during the long sunless winter. So that's where you get all of your equipment, like snowmobiles, tents, all that kind of stuff. All the clothing you actually collect from the place in Christchurch. And here is Antarctic Field School, day 1. We're inside and we're learning some basic techniques about how not to die in the Antarctic. And it's absolutely essential to have some basic mountaineering skills. And here we're learning crevasse rescue, both self-rescue and also if you have to bail out one of your teammates that has fallen down a very, very deep crevasse in the ice. And since we're going to be out on glaciers and other extremely snowy places, that's absolutely essential that you have those sort of skills, both how to avoid winding up in that situation, but also what to do if you do find yourself down a crevasse. Here's a crevasse. This was not one that I fell into, but one that we practiced hoisting each other out of. And so they lower us down there, and you basically, using the skills that you got just the day before, you have to sort of jimmy yourself out of there. And so that was a lot of fun. And also we had to practice hoisting our pals out of there, because if somebody hit their head and was unconscious and they weren't able to self-rescue, then they would have to get bailed out by the teammates. But some of these could be quite deep. These were, some of these were like 100 feet deep, and you just, kind of hope for the best when you're out there, but definitely prepared for the worst. Here's some more things they don't teach you in graduate school. Learned how to ride a snowmobile. Being from upstate New York, I actually had been on a snowmobile at some point in my life, but I never actually driven one myself. It's quite a different animal when you're the one driving. And so we had to learn how to kind of go up these really steep slopes and over some pretty crazy terrain and not flip the thing over or otherwise do something crazy. And also you have to be able to put those snowmobiles in the only transport that is available if you are doing field work. Well, actually, there's 2 different kinds of transport. One is helicopters, the other are these twin otter planes. And the twin otters are actually the larger of the 2. You can't put a snowmobile in a helicopter. So what we're looking at here is a little ramp, and then my teammates trying to shove this thing on the airplane, and this is actually somebody driving it. So it's a combination of driving it very gingerly, giving it a little gas, and everybody else pushing and shoving that thing into these twin otter planes. And everybody else always wants to know about the weather in Antarctica, and the fact is that it changes. It's kind of like saying, what's the weather like in the United States? Like, well, it depends on where you are, and it depends on what the weather is like on that particular day in that location. But it's pretty cold overall. This was actually a screenshot that one of my pals who was on the team that went through the South Pole. I personally did not get a chance to go to the South Pole, but I feel like I'll explain more later, but I got the better deal. I was happy to not go to the pole because I got to do some other really cool stuff. So, but yeah, minus 39 degree wind chill, that's Celsius, but when you're talking about minus 39, Celsius and Fahrenheit are pretty much the same if you do the conversion. The wind can be absolutely wicked out there. The mechanism that drives the intense winds in Antarctica is, they're called katabatic winds. And katabatics are these gravity-driven winds. What you get is a cold, stable air mass sitting over the South Pole, and the ice is very thick at the South Pole, and it flows towards the margins of the continent. So there's this net downhill kind of slope going from the South Pole to the shoreline. And so what happens is that every once in a while this normally stable cold air mass gets a little destabilized, and you get these gravity-driven winds that just kind of go barreling northward. And if you've ever been standing in wind that was coming straight from the South Pole at about 40 miles an hour, then you really know what cold is. Didn't snow very much. This is the equivalent of the Sahara Desert. It's probably drier in terms of precipitation than the Sahara Desert. So, we didn't have to shovel snow very often. But when you have wind like that, a little bit of snow can get all piled up in one particular place, which can also be pretty fun. So let's talk some more about the actual collection process for these meteorites. What happens is that the meteorites that fell many, many years ago, so we're not looking for meteorites that fell yesterday. The majority of the meteorites that they collect in Antarctica have been on the surface of the Earth for about 25 to 65,000 years. And that time frame corresponds to roughly the amount of time that has occurred since the glaciers, because we currently live in a warm interglacial period, believe it or not. And so 65,000 years ago, the planet was much more heavily glaciated. There would have been glaciers in Oregon at sea level or close to it at around that time frame. But since then, the planet has been warming. We've been conveniently speeding it up to the thrill of meteoritists everywhere for the past 100 years or so since the Industrial Revolution. But in these intervening tens of thousands of years, all the meteorites that fell during that time frame are now being exposed at the surface of these, essentially fossilized snow in the form of glaciers. And the average age of the rocks themselves, since they were formed from essentially gas and dust in the early solar system, they're about 4.5 billion years old. So that's essentially the same age as the sun. And what happens in Antarctica is that meteorites that fell over a large area actually get concentrated due to a combination of the ice flow as these glaciers are slowly flowing towards the coastline of Antarctica, and also these absolutely brutal winds that are blow very often are essentially scouring away, ablating away the ice from the top down. So if you can picture this, over tens of thousands of years, snow is falling, the occasional meteorite falls. It's kind of like this raisin bread of, mostly snow and the occasional meteorite. And then as the snow piles up and doesn't melt like it does if it snows here or, in somewhere that's not glaciated, it gets compressed. So you get tens of thousands of years of snowfall getting compressed like this. So now your raisin bread is like a raisin pancake, but it still has the same number of raisins in it. And as this raisin pancake sort of slowly oozes towards the coastline, there's certain places where the ice actually stagnates. And as the wind blows, that's like blowing away the bread part of your raisin bread, just leaving the raisins stranded at the surface. And so when you drive along on a snowmobile on the ice, which involves these things do not have shock absorbers, and they weren't really designed for ice, but what are you going to do? You don't really have a lot of options. But as you drive along, there's like rocks laying around. Some of them are terrestrial rocks. You can see that, it's not that it's just one giant skating rink without any land in sight. There's definitely rock outcrops, mountains, and all that kind of thing. So sometimes it can be really confusing. It'll be mostly terrestrial rocks with the occasional meteorite, and then there's other places that there's absolutely not a speck of dust for, miles and miles around, and then you see a rock just sitting there. And actually those rocks were discovered in the early 1900s when the polar explorers like Shackleton and Scott and the other explorers that went into the area, they actually found these rocks laying out there, and they were like, wow, where did this come from? And just out of scientific curiosity, they would pack it up along with the penguin eggs and whatever else they were finding. And they didn't recognize at the time that those things were meteorites. But then, as they sat in collections and other people examined them, they realized that these were meteorites. And then, ultimately rocks are pretty easy to see on the ice, so it doesn't really require any particular scientific expertise to look at this, rock sitting there with no other rocks for miles around. So here's Antarctic exploration back in the early days. The Norwegians were creative in that they brought dogs, and so they went by dog sled, being good Norwegians. The other side of that coin was they wound up eating their dogs as well, which was a pretty grim circumstance and kind of indicates the sort of hardships that people suffered there back in the day. The English, being good, upstanding, stiff upper-lipped Englishmen, just man-hauled these things, these big, you can see these guys schlepping these things. They also had ponies and stuff like that. The ponies also made a pretty good hamburger on the grill at some point. So. But in modern times, it is actually illegal by international treaty to bring any kind of animals to the Antarctic continent. Needless to say, no animals, including people, but animals don't fare very well there. It's just very difficult to, keep them from, just keeping them comfortable just by basic standards. So this was our setup, which was like absolute luxury compared to what they had back in the day, and so what we've got are snowmobiles, and the tents that we lived in were pretty much of the same type that Robert Falcon Scott would have used back in 1909 and 1906 during those early expeditions. 9 foot by 9 foot square, kind of like a teepee shaped, and they stand up pretty good in the wind. You might notice that the little doorway is kind of bulged out. That's because the wind actually is blowing it, and normally this was just a little flap that would hang there, and it's like a little airlock kind of a thing. But in a strong wind, which was most of the time, these things would kind of bulge out. And we have a solar panel, and that's useful for charging up your iPod and kind of passing the hours when the weather is bad. And we've got, here's a little radio antenna, so we were communicating by radio, and we had to set that up every time we moved our camp. And also keeping food from, going bad is actually pretty easy. The problem is there's some things that you actually don't want to freeze. I can tell you that mayonnaise is really bad if you freeze it. Salsa was not a good idea in the field. The salsa actually exploded all over everything. That was a lot of fun. But we had like salsa flavored everything for about a week. Hey, breakfast? Yeah, a little salsa on it. So, but anyway, it was pretty mellow. People also want to know, how do you go to the bathroom in the Antarctic? That's always the top question I get from the kids, and it's a very important question. And you can imagine in a place that is so cold that your food would never, they're finding food, canned food that was left over from the Antarctic explorers of 1902, and they're finding that stuff, and it's still, I wouldn't call it fine, it's probably a little dried out, but it basically, you can still look at it and tell what it is. So you can imagine what all other kinds of things people might leave out on the ice. And so when you do field work in the Antarctic, it's sort of pack it in, pack it out, and so, yeah, so it gets interesting. But we have ways of dealing with all of that, and it actually worked out pretty good. The one thing you don't really have is luxurious showers and that sort of thing. So liquid water is a precious accommodation. The way we got our water was to take big hunks of rebar and hack out big chunks of ice, and then start the very, very slow process of melting it with stoves. And if you've ever melted like even a gallon of water that way, it takes forever. The amount of fuel it takes is absolutely staggering. So here we go. Here's the Scott party at the South Pole. This was the ill-fated expedition where they got to the South Pole and they found that the Norwegians had already been there. So Roald Amundsen and his party had already been to the South Pole, and they found mittens and other supplies where they were like, oh, thanks. So there were actually 5 on this expedition, and they did not make it back to safety. So their bodies were later found, and so there's a memorial and everything at the South Pole. It's really interesting. So here's the Antarctic search for meteorites. That's the ANSMET acronym. So here we are enjoying a little break, and you can see what kind of face gear we wear. it's basically a motorcycle or a dirt bike face guard and outfitted with a reflective visor here fitted into ski goggles. And that was absolutely essential because the light is absolutely blinding down there. You might think, well, it's at the extreme latitudes. The sun isn't as strong there, but the problem is the sun is in your eyes all the time. It's like always right here at eye level. And this is a Cliff Bar. Just so you know, Cliff Bars are not recommended. They take on the consistency of a hockey puck in the cold. And so those of us who brought Cliff Bars with us to eat wound up wearing them in our armpits for most of the day and then take it out and eat it real quick. So we come up with solutions to all kinds of things. But it was pretty cool to go to some places that no human being had ever been before. And I don't know which was cooler, going to a place like that or going to a place that the only person who had been there before us were these parties of Amundsen and the Scott expedition. So that was pretty neat, regardless of which way that was. And so what we're looking at here is a map of particularly rich meteorite hunting grounds. So they have numbers here, but these are places, a couple of these places were where we went the year that I went, but there's also a couple of others that had been visited in previous expeditions. And what happens is that you get snow falling all over the continent, and even though it's not a lot of snowfall, the fact that it never melts means that it just piles up. So the ice is 2 miles thick at the South Pole, which is around here somewhere. And ice actually is a fluid, believe it or not. We don't really think of it because in our time scales that we think about, you don't see ice flow. But ice is like a very, very gooey fluid, like toothpaste. So you might put a blob of toothpaste on your toothbrush, and it looks like it just sits there, but if you come back 15 minutes later, it's kind of like mushed down and kind of hanging over the sides of your toothbrush. Well, ice does that over thousands of years. And so it's slowly oozing towards the lower elevations, which is the coastline here of Antarctica. But along the Transantarctic Mountains, which is the mountain range that pretty much bisects the continent, the ice has to kind of squeeze through these narrow mountain passes. And what we have are these stagnation areas. So the ice will speed up in a glacier and it moves fast through the mountain pass, but on the other sides, like just on the mountains that actually block it, the ice actually pools and kind of sits there and sometimes has almost like a circular, like a very, very slow eddy. They actually see this in the ice. And those are great places to search for meteorites because those areas have had many, many thousands of years of wind just blowing and blowing and blowing. And so when the geologists scope out the areas to look for, places that the geology says that this might be a rich meteorite hunting ground, that's exactly what they're looking for. And here's another little cartoon that describes what's going on. So the ice just has a net overall motion towards the ocean, and in places where the meteorites are found in great quantities are along these where the ice flow is slowed down because of the mountains. So you don't want to look for meteorites here on the glacier, you want to look for them here on this ice patch that has just been essentially very, very old glacier ice has been exposed to, the elements essentially. And what happens when ice is compressed and has all of the air squeezed out of it, ice is actually not clear, it's blue. And the background that I'm using in my talk is a close-up picture of the ice. And it actually radiates this blue color. It's not a reflection of the sky. We saw the most intense blue on days that it was completely overcast, kind of like today. And so that is ice with most of the air squeezed out of it. It's extremely old ice. And if there's any physics people, I know we've got some physics people in here. This is due to Rayleigh scattering. Same reason that the sky is blue is why ice is blue, except it's the water molecules instead of the nitrogen molecules in the air. So here's a picture taken at a pretty high altitude, and just locations of particular meteorites that had been recovered over the years. So we actually visited this area. The DOM designation stands for Dominion Range, which is the range of mountains that comes through here. And whenever you see a landform that kind of looks like it has this sort of round almost a scalloped edge to it here. That's the toe of a glacier, and the glacier essentially stopped there, and then it leaves this kind of like a bathtub ring. When you're really dirty and you get in the bathtub and the water slowly drains and you get that little grungy ring? That's the same mechanism here. As the glacier shrinks back, it just drops whatever rocks it had been carrying with it. So you get these bathtub rings of all kinds of rocks, but when you take a closer look, you find actually a lot of meteorites, because there's been an awful lot of ice that has vanished from an area like this. And so we found a lot of meteorites in this little area here, and also scattered around through other locations, but this one was visited in 1985, and then we went back in 2003, 2004, and we found a lot more in this area. And here we are another day at the office, driving along on a skidoo and checking for meteorites, and that really is how we do it. Depending on exactly what the terrain looks like, you're basically far enough apart that you and the next guy can see pretty much anything as big as a Hershey's Kiss or bigger. So we all know what a Hershey's Kiss looks like. And so if you're 50 feet away, or the width of this stage, you're probably a little wider than this, on essentially white ice or very bright ice, you can see something the size of a chocolate chip on that ice. It's pretty amazing, especially once you sort of get your eyes tuned for it. It's just like with many things, it's a skill that gets better with practice. And so we would just do this for hours and hours and hours. And then when you find a rock, you stop and you look at it and you wave your arms like this, and then everybody comes over. And if you see something that looks like this, that's when you get very excited, because this is a rock that burned. And there's only one way that a rock, at least, not that somebody has artificially messed with, there's only one way a rock burns, and that's as if it is moving at extremely high velocity, like hypersonic speeds through the atmosphere. And when it does so, all the jagged edges get fried off, and it essentially makes this thin crust called a fusion crust. And that black crust, it's very easy to flake it off. It has the consistency of almost like glass. And so it's very friable. The rock underneath it is like a chunk of concrete. And so it's pretty exciting to see this. And you can even see some of the chondrules, which are little like glassy beads that are about 1 millimeter in size, from anywhere from 1 to 3 millimeters in size. And they're actually very common they make up the bulk of the most common type of meteorite. I have one of those that I can show you here. But just before I forget, the meteorites that I have here are not Antarctic meteorites. They're ones that I bought off the internet just for, educational purposes. The meteorites that we collect here belong to you, the taxpayer, who funds these trips, and they're curated at the Smithsonian Institution in Washington, D.C. All right, so when we find that rock, what do we do? Well, don't step on the crevasse. Crevasses come in all shapes and sizes, and this little thing with the fluffy kind of consistency, it's very harmless looking, but it's actually a very deep crevasse, and you're not going to fall in it, but it'd be really easy to twist your ankle in here. And when you are probably 8 hours from any kind of medical attention other than very rudimentary, field medicine, you really look carefully where you step. So that's the first thing. You can see that it isn't exactly, look at that really is about the size of a Hershey's Kiss, but we pick up everything we see. And this right here is a GPS, and this isn't like the GPS that you have in your Garmin or in your car. This GPS is more like of a military grade GPS. Like not everybody can get their hands on this kind of technology. Even a decade ago, this was only if you had a really, really good reason to have it. And as geologists working in Antarctica, that was a pretty good reason to have it. So this allows us to pinpoint the location of the meteorite within less than a 1 square meter area. And so we do kind of like to make sure it's a meteorite, because there's some places where there is a lot of terrestrial rock, earth rocks laying around, and you don't want to bring home a ton of earth rocks in one meteorite. So you have to do some, triage out there in the field. And we don't have enough room in the boxes and enough freight to be able to take every single thing home with us. But, you know, most of the meteorites out there they're so jarringly different from whatever the terrestrial rock is in the area. And I'll show you a couple of examples of, you know, where they are really obvious and then where they're not really obvious. So, so we take the GPS position and field number and a photo, just some basic field work kind of things. Just take a ruler and it's like, okay, it's roughly 3 by 4 by 7 centimeters or something like that. Place it in a sterile sample bag. The next time that these meteorites see the light of day, or that a human being will see them, is when they go to Houston, which is where the NASA facility in Houston, Johnson Space Center, has an astromaterials curatorial facility. So that's where they do like the first cut. They take the meteorite out and they have people who characterize it and group them into the different types of meteorites. And then from there they go to the Smithsonian Institution, where especially the samples that are particularly interesting, like lunar and Martian samples, are also kept there. All right, so scientists at work, it could be anything. This could be ants, it could be archaeological things. It's all the same, right? People hunched over things. The only difference here is the snow blowing by. You can kind of see. So that was just another snowy day. You'll notice these extremely stylish boots. They look like Bugs Bunny feet, so we call them bunny boots. And they actually do keep your feet warm, oddly enough. I mean, warm as in not frozen, not warm as in comfortable. Here's a really interesting geology shot. What we're looking at is the location where this glacial ice meets the local bedrock in the area, the mountains that are in the area. If you were hiking in the mountains, this type of a feature is called a Bearish Runt. It means a mountain skirt. And so basically it's the very deep crevasse that you typically get right at the starting point of a glacier. And you can really imagine, you can almost follow the slope here where this, the snow would have actually covered up this mountain, which is why, it's not a pointy mountain, it's just sort of a rounded shape here. And over tens of thousands of years, this glacier has retreated, leaving behind this mountain that it used to grind over for many, many millennia. So this thing has been ground, not smooth. It's basically a big pile of rocks, but it's not a pointy mountaintop anymore. And as the glacier recedes, it leaves this very, very deep crevasse. On one side is ice and the other side is rock. But here's one of my teammates right here. It gives you an idea of the steep wall here and how high it is. So this is probably 40 feet high. Also, you don't want to be on a snowmobile here because it's ice, and if you're standing on it, you will slide. Like, there's nothing to grab onto, nothing to stop you. So, there's potential hazards working in these areas. The cool thing about Antarctica is not just the meteorites, but there's actually a lot of fossils. They find petrified wood in Antarctica. They find dinosaur skulls, and the dinosaurs have these humongous eye sockets and these lobes in the back of your brain that process visual information in all vertebrates. And so they find these dinosaurs that they must have been living in a warm climate. The fact that you have something that may or may not be warm-blooded and big animal living in a place that was polar. We know it was polar because they had very, very long winter nights, but it must have been temperate. So one of the other things that we found here was that this rock actually was full of fossilized sea creatures. So all kinds of neat stuff that's found there. Here's an example of a carbonaceous chondrite. So the more than 90% of all meteorites are what we call ordinary chondrites. Ordinary because they're so common among meteorites. And the chondrite, again, are those little chondrules, those little glassy beads. And the carbonaceous ones are particularly interesting because they have a lot of organic compounds, including some of the nucleic bases found in DNA. So thymine, uracil, guanine, and cytosine have actually been isolated from carbonaceous chondrites. Just absolutely cries out to imagine the possibilities there. The basic ingredients for life. Also, 70 different amino acids. Not all of the 23, I think it is, that are used by life, but 70 different kinds of amino acids have been isolated in these types of meteorites as well. Here's one that was pretty cool. So the chemical composition is kind of, run-of-the-mill garden variety as meteorites go. But this is oriented, and it has the same shape as, can you sort of picture the space shuttle? How the space shuttle doesn't have a pointy nose like the Concorde, it has like a blunt nose. And that is actually a mathematical, you can calculate mathematically what that shape is. And so this meteorite already was kind of pointy when it came into the atmosphere, and as it did so, it ablated away into the shape of what, hypersonic rocket would take, like the space shuttle. So instead of just tumbling in all directions as it came in, which most meteorites do, this one sort of stayed oriented and maybe rotated a little bit, but stayed kind of heading that way. And you can even see the flow pattern on here. That was pretty cool. You get these streaky kind of, I think you can even see that. Can you kind of see that? These sort of streaks. That's when molten rock was just like peeling off of it, like little droplets of rain off your windshield. Here's a couple of other weird ones. This, I'm not sure what this one turned out to be, but it didn't look like anything else we had found, and we found it in a place that there was absolutely no other rock. This one turned out to be a Martian meteorite. We didn't know it for sure at the time, but one of the meteoriticists that was in our small group of 4 people, he had his suspicions, and he was standing there looking at it, and you could tell he was pretty happy, but he wasn't really letting on what he was thinking. And but that was a pretty exciting find, and it was also really cool that 6 months after I got back from the trip, I saw the picture that I had taken, and it was on CNN, and it was like, Martian meteorite found in Antarctica, and I was like, hey, I took that picture. That's pretty cool. And people often ask me how we know if they're from Mars, and some of them are a little easier to find than others. But actually, the way that we determine that it's a Martian meteorite, I didn't bring my slide with me, but what they can do is actually extract gases from these little bubbles of air that are in the rocks. And when you have a meteorite that even has these little bubbles of air at all, it says that it comes from somewhere with an atmosphere. And when they analyze those bubbles of air, they don't have the breakdown of gases that we have here on Earth. They actually have the exact breakdown of gases that's in the Mars atmosphere. And we know Mars's atmosphere really well because we sent a whole bunch of spacecraft there over the years. Here's another meteorite. This one we were pretty excited about because it did not have chondrules in it, as the Mars meteorite did not either. So these chondrules are, they're so indicative of like, ho-hum, another meteorite, that when you see one that doesn't have it, it's like, ooh, cool, this one doesn't have chondrules. So this one did not have chondrules. And it also doesn't have as shiny a crust as some of the other ones. So that was also kind of interesting. Here's another one. I guess these are chondrules, but like the white matrix was something that looked a little different than some of the other things that we found. All right. So this is actually a map of an area that we searched. We went to all of these ones that I've circled in black here. And when we got to this place called the Otway Massif, we knew that there were a lot of meteorites there. About a decade before we went, a team had been down there and said, oh, this is ridiculous. There's like many, many tens of kilograms of rock here. We can't pick it all up. And they just took one. They figured, some ANSMET team in the future can take the rest of it. So we went in there to clear that area out. And long story short, I wound up being part of a research article that just finally came out 2 weeks ago. And the significance of the discovery here is that it was the oldest strewn field, which is, so a strewn field is what you get when it's not just one meteorite that plops down, but it's a larger object that fragments into a whole bunch of smaller pieces. And so those pieces had scattered all over here, but they were still arranged in the same way that they had fallen. And so that was really interesting because it tells us about the ice motion in that area. Like, what has the ice been doing for the past, tens of thousands of years? Because this thing sat on the Earth for a long time, but the ice motion in that area hadn't disturbed the outlay of the meteorites. So what we found was that, so what happens is when you have this larger object come into the atmosphere and fragment, it's kind of, imagine a big hunk of something heavy moving at a very fast speed, and then you have smaller, that are essentially acting like pieces of dust. And the smaller pieces are affected by the drag forces of the atmosphere much, much more so than the big pieces, right? Like a cotton ball is totally affected by the air around it, whereas a golf ball is not. So what winds up happening is that when a meteorite comes in and breaks up, the big pieces just kind of go furthest downfield, where the smaller pieces kind of fall short of that. And so you get this strewn field. And that had remained intact over these many, many tens of thousands of years since the thing fell on the Earth. So it took us a few days to pack it all up. There's a little flag. You can kind of see these little flags here everywhere that we picked up a piece of meteorite. All right. But the funny thing about this was that the meteorites looked very much like the rock that's in the area. So the native rock in the Grosvenor Mountains, which is where we were, is called Dolerite, and it's a volcanic rock. It's a form of basalt, if there's any geology fans in the audience. And it weathers to sort of a reddish, rusty-colored rock. And our meteorites had also weathered to a rusty, reddish-colored rock. So here's a piece of the local rock in the area, and this is the meteorites. In fact, when we got to the area, we're looking for meteorites. We were looking for black rocks. We didn't know it was a strewn field. We didn't know it was a single object. All we had were field notes from 1985 that said there's meteorites all over the place. And we're walking around, and we're like, where? I mean, we thought we were walking on this. There was a lot of this stuff laying around. And then at some point, somebody picked up one of these, and the other side of it was black. They had that fusion crust, and we're like, oh, that's what they look like. And then as soon as we recognized what was going on, then we were like, oh, there's one, there's one, there's one. And then we cleared it out in a couple of days. So here's a map of the GPS locations of everywhere we found fragments. So every blue dot is just when the GPS went ping, and every pink dot is where we stopped and picked up a meteorite. So you can kind of see how we sort of drive around all over the place, but once we found this, we went back and forth over it many, many times. So some of them had absolutely no fusion crust on them. They just seemed to be an object that broke up when it was pretty low in the atmosphere and wasn't moving fast enough that every piece had it. But some pieces had quite a bit of this black crust, and others had none at all. So it was kind of, we spent a lot of time sort of puzzling over exactly how that happened. Here was the largest fragment that we found. This rock weighed about 60 pounds, and we've got just one little patch of fusion crust on there. And and then here's the little counter that just gives that rock a unique identifying number. So that was kind of fun. We had to, jockey these 3 pieces of rock that weighed, 60 pounds. I think the heaviest was 60, and then there were 2 others that were like 30-something apiece. And that's hard. If you ever try to pick up something that heavy, that's hard. That is not a one-person job. So here is my tent mate, Gretchen Benedicts. She's a meteoriticist now at Curtin University in Perth, Australia. And we're sitting next to one of these little things and just taking a little breather. The fact that we're dressed like this and not with the full face mask indicates that this was actually quite a nice day by Antarctic standards. Another interesting mechanism to concentrate meteorites is by wind, by actually physically moving the meteorites from, the fact that the wind is blowing and it'll blow it along. So you can imagine, wow, if rocks are blowing around, that must be some pretty serious wind. So this was like an ice skating rink. There was not a speck of dust out there. And so we're driving along, and all of a sudden we saw like this patch of rocks here. Most of it was just plain old rock that fell out of these mountains over here. But we probably found about 50 meteorites in this little, it wasn't an area much bigger than this stage, and we found 50, and they were all almost exactly the same size. So Mother Nature and the wind had conspired to move rocks that were exactly this big. Anything bigger didn't move, anything smaller blew away, and everybody else, this big, sat there. That was kind of cool. Some nice physics at work there. But then began the game of meteorite or meteorong. And I have an example of meteorong up here too. We'll see if you guys can tell the difference. So yeah, we're looking at these things going, okay, well, we've got a few hours to kill, and that's what we did. So I went over that literally with a fine-tooth comb. There is a meteorite in this picture, and I'll give you a hint, it's not this. That's a little pocket knife. But you see, you just play one of those, the game, one of these things is not like the other, right? You see something that looks a little out of place. Just holler it out if somebody's got it. Yeah, like right here. Tell me if I'm getting warmer, colder, down. There we go. That's right. So that's a meteorite. See, I mean, it really is that easy. That after listening to me yap for a couple of minutes, everybody's an expert meteorite hunter. And there might have been another one in this view too. But yeah, I mean, they really kind of jump out at you. Smoothed off. They've been fried. They don't have this jagged appearance like some of these other rocks. All have sort of, they're pieces of broken mountains. But this is not. All right, and we've actually got a couple of meteorites in here too. Also, here's a scale bar. This is about an inch right here. There's actually two in this picture. So I'll start in the middle and tell me to go left, right, up, down. Down? 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 Left? Your left or my left? This left?
The other, there.
That left?
Down, then the other way? Yes.
That?
Yes.
Okay, well, it's true, it doesn't look like the other things, but most meteorites have that black fusion crust, right? So we're looking at something that's a little bit blacker. This is weird. It's a weird looking rock, but it's not entirely outrageous. It also has a lot of jagged edges. So this thing did not burn, right? All right, so let's start here. Which way do you want me to go? Left, right?
Up.
Up?
Up.
Left?
Or not open.
Up?
Left. That one.
Okay, cool. Anything else? Uh-huh. That? All right, let's see if we're right. All right, cool. Got a little led astray by this one that looks different. I'll admit that would have caught my eye, but these are our meteorites. Good. The other thing that people always ask me is, why don't we use robots and stuff? And, robots are expensive. Graduate students and postdocs, we work for free, we're almost free. Just feed us something, make sure, you don't freeze, and we're good. So it's actually pretty cheap. And human beings, there's nothing that beats the human brain. There's no robot that you can program to do what a human brain does. And I know we're in Silicon Valley, and I gave this talk at some kind of little fancy, startup. They were like, hey, and I'm like, no. First of all, your little robot, as soon as that breaks, we're done, right? And things break in the cold. All kinds of horrible things happen to machines in the cold. People get a little cranky, but, we can still function. They actually have tried to use robots in the Antarctic, and the robots get distracted by every little shadow. It's like, oh, a dark thing? Oh, this shadow. And it'll get stuck, analyzing this shadow for 20 minutes, when everybody else is like, come on. Right? So people are just really, really good at doing this. And it's one of those things that it's really hard to explain. If I had tried to explain to you without showing you pictures and stuff in the beginning of the talk, that would have been really hard to pick out those meteorites in that slide I just showed you. But just after listening to me talk about it, it's like, oh, okay, well, there it is. And you just can't get a robot to do that. Maybe someday, but they're still really expensive and they're heavy, and you still have to have a person go with it to, program it and shut it off and on and stuff. So the bottom line with working in Antarctica is keep it simple. Send people, send a minimum of equipment that you have to rely on, because if you're relying on super fancy stuff, anything more fancy than a GPS, then you're just asking for trouble. It's very expensive to keep people, well, not as expensive as robot, but it comes out to about $10,000 per person per day. So it's like staying at, not even a fancy hotel. We're talking like a really fancy hotel, $10,000 a night. But that's, when you add it up, it's like, wow, we're getting samples of other worlds that we would have to spend hundreds of millions of dollars on a space mission to a comet or an asteroid. And even though we've had missions like that, and they do cost hundreds of millions of dollars, you get a little bit of dust back. You don't get 40, 50, 150 pounds of rocks on a space mission, with the exception of the Apollo missions. Here's some more just gratuitous, beautiful scenery. The Antarctic really does have some of the most incredible scenery. I've been to a lot of places in the world, and there's just nothing that even comes close to seeing a glacier just kind of crumble and fall apart here. I was in New Zealand after the trip and went to see some glaciers in New Zealand, and it was pretty cool. They've got some awesome glaciers that kind of come down into the into the jungle and stuff, and there's a big river coming off the end of it. But in Antarctica, the glaciers just end, boom, and some crumbled ice. This is actually a huge cliff face. It's probably 40 feet high. This is one of our teammates standing there admiring the view. There's some really interesting atmospheric phenomena that happen in the Antarctic. Every once in a while, we see a halo around the sun. Have you seen this? Like, you've seen a rainbow? Like, it's almost like a rainbow. You can make out a little bit of color. And we saw that quite often in the Antarctic, and that's because the sun is always at a really nice height for that. When you're at extreme latitudes, the sun doesn't get high overhead like it does here. It's always like right around there. And when it's only 20 degrees above the horizon, you actually get some really interesting effects with the clouds and the ice particles that are in the air. So we see some, this is a sundog, this is the 23-degree halo, here's a upper tangent arc. We saw a lot of really interesting displays. But at the end of the day, the take-home message from this is, I think, best to quote Dr. Seuss, who was quite an authority on a number of things that pertain to life. If you want to catch beasts you don't see every day, you have to go places quite out of the way. You have to go places no others can get to. You have to get cold and you have to get wet too. All right, thanks very much.